Hi, good morning, everyone. So my name is Zijian. I'm currently work as a lecturer in the School of Electrical Engineering and Computer Science. Previously, I have been privileged to work with Professor Scott Chapman and also the analytics for our Australian green industry team to broaden my knowledge on the agriculture side. So my original background was in computer vision and multimodal AI. So today, I will talk a bit through on the topic of the semantic segmentation. So first, before I introduce the technical term of the semantic segmentation, I would like to know about first, what is semantic segmentation? And second, in the general domain, let's say what semantic segmentation can bring forward to us, right? First, what is the task of semantic segmentation? So semantic segmentation is you assign a class level label for each one of the pixel within this image, right? So we have shown a few examples here. So on the first one is in the civil engineering scenario, right? So in this case, we want to identify the cracks on the road. So then we perform the semantic segmentation to segment out the cracks on the road. And then we are able to measure the area and the dimension of those defects on the road. This is done by several different things. First is semantic segmentation, and second is we have the known camera setting. Then we can just directly compute the area affected. And then on the bottom middle, so it is the image and it is the SEM, so it's the macroscope image to identify the different components, right? So in this case, we want to measure the component of the percentage of two different chemical compounds under the SEM image, right? So and then in the top middle, so we are trying to measure. Okay, so where is my specific speculate, and then what's the percentage of speculates affected by different disease or stresses, and then on the that should be my right hand side. It is also a SEM images. This comes from the collaboration with one of the mechanical engineering. We want to measure the smoothness of the grinding, right? So in this case, we can use semantic segmentation related method to detect that. So I believe we have a good motivation on, okay, so first, what is the semantic segmentation? And second, what semantic segmentation can bring us in the general domain, right? So this is the outline of today's talk. So today's talk, I would like to split it into two different sections. So one, in the first part, I would like you to walk through the development of the semantic segmentation in the computer vision domain, right? So we jump back to the 30 years ago, see what segmentation looks like back to then, and then how it developed until now, right? And then on the second part, after we have a good general knowledge on the semantic segmentation, I want to bring you into one of our recent work on how we leveraging this semantic segmentation to solve the agriculture problem. This, you may find that the title is similar to what Dan has recently just show us in the morning. So it is second version of the Global Wheat project. It's called Global Wheat Full Semantic Segmentation. Right? Without further delay, so let's start with our first part of today's talk. So back to 30 to 40 years ago. So back to then, we don't have any deep learning method, and AI was not a buzzword back to then, right? So if people want to do the segmentation, what they're trying to do, right? So first, for example, they have a input image like labeled as the original here. So they want to segment the foreground and background. What will they do, right? So they will have a statistical analysis about the pixel intensity, right? So and then they put up a histogram and then find a best threshold by maximizing the inter-class separability and minimize the intra-class techniques, right? So by optimizing these two criteria, they find this threshold colored in the red. And then by using this threshold, like let's say if your intensity is lower than this threshold, you belong to the background. And then if you are stronger than this threshold, you are foreground, right? So for some cases, it can do the job, right? So let's think about one of the naive example in the agriculture domain, right? So we want to separate out the grain coverage. So grain coverage on the land. So in this case, we can use the simple as thresholding to find the threshold on the color channels, and then to split out the grain cover and the land itself, right? So those methods involve no AI, no deep learning. It's statistical method, right? But that's not the end of story. So what's good about the traditional method? First, it's super interpretable. And it is mathematically grounded, right? So it works on the simple, well-lit, low noise images. But there are quite a few limitations, right? So the most important one is it's actually just segmentation. It's not the semantic segmentation. Why? Because we can only tell it's foreground or background, right? So if we have a look at the example here, so let's say I would like to segment out each individual car. Can the traditional method do it? No, because it can only split out the foreground and background based on the color intensity. So those are the segmenting results by applying the traditional method. Apparently, it can't do the job. So what we are actually looking for in this question is to segment out each single car. In this case, we want to move forward, right? So we needed method that could learn robust feature that can do it automatically, right? So then let's dive into the let's say last decade, right? So it starts from late 2000s and then up until now, right? So deep neural network. So before we introduce a bit too much about deep learning work, let's just have a look of this simple case, right? So image classification. We want to assign one label for the entire image. In this case, we don't care about those pixel level labels. We only assign one label for entire image. So this is a very naive neural network, right? So give an input image, and then you have a what we call kernel to scan through this image, right? And then after this scan through, it forms the what we call the feature map, right? The feature map is the representation in the latent space, right? And then we can do more convolution to downsample this feature map. We can also do pooling, different method. But in the end of the day, we can see that it forms a dense vector. So this dense vector is the representation of your image, right? And then it's the classification you classify on this dense vector. So this is how the deep neural network, at least in the computer vision domain, works. But what we want to try to tackle is semantic segmentation. As we mentioned, the task is to assign a label for each one of the pixels, right? So in this case, we are not thinking about one pixel per image anymore. It's the one label per image anymore. It's one label per pixel. Let's just take one pixel out of this entire image. Can you really tell which class it belongs to? No, I can't tell. You can't tell. We can never tell about it, right? So what is this pixel? What is this patch? We can't really tell because what we are missing, we're missing the context. We don't know where this pixel, where this patch comes from. So that's the reason why we need to increase the context information, right? So we need to understand a bit more that is surrounding this pixel, this patch. A naive solution coming from the image classification is we can crop a lot of patches from this image, right? So, and then we do a classification on it, and then we assign this image label to this center pixel, right? But how many pixels do we get in the image? A lot, right? So if we do that kind of classification, that's a big waste of the computational resource. And then maybe it won't get us a good performance as well. right? So because they are not reusing the shared features between those overlapping patches. So what people will do? People will just encode those images into latent representation again, like what we did in the image classification. With those kind of context information, now people can do the classification on the pixel. A rough structure could be, okay, we have a image, we passing through some convolution, we downsample, get the global context, and then upsampling to the original feature dimension, and then do the classification. So this is a method that published in, I believe, 2015. It is one of the first method that is using the end-to-end convolutional neural network to do the semantic segmentation. What it's trying to do from the right-hand side, you can see it quite clearly. It's gradually downsample it to a very dense vector from the image to feature map to the vector, right? And then they upsampling the vector to the original dimension, and then doing the pixel level classification on those each single dimensions, right? So, and then you will form this kind of feature map, right? So that's the first work basically for using the CNN to do the semantic segmentation, right? So that was 2015, and then with the technique improvement, people are exploring different methods like UNet, DeepLab V1 to V3, V3 Plus. I believe DeepLab V3 Plus is still one of the most useful and classical method with the CNNs as the backbone neural network, right? But recently, I believe most of us had heard of the buzzword transformer, right? So now a lot of different methods are building on top of transformers. LLMs is a very good example here. And transformer, the design of the transformer, self-attention mechanism also affect the design of the computer vision community quite much, right? So after the rise of the transformers, we have also a revolution in the segmentation domain, right? So we have methods like the segformer, we have this method like the mask-to-former, we have methods like segment anything, SEM, right? So they are all based on transformers. But what is the fundamental difference between the CNNs and transformers, the self-attention mechanism? Let's have a look at this comparison here, this animation. So previously, we talked about one issue is the context, right? So with a convolutional neural network kernel, the context you will get is the size of that kernel, and then stacking up, and stacking up, right? So it's gradually increasing it. It will get it, some of it eventually, but you will see the mechanism is different. When self-attention do it, it's like, what is the relationship between my patch and all other patches, right? So it is not limited to that kernel anymore. So based on the self-attention mechanism, the context can be just directly broadened to the entire image. So that's the key difference of the self-attention mechanism and the convolutional neural networks. And then I will just skip some of the representative work in the transformer domain. So I will just quickly talk about segment anything before I dive into second part. So segment anything. So this is the framework proposed by Meta on 2023. And then they recently just proposed SAM 2 and 3, right? So SAM 2 and 3 with all those combined family, now it can do the image segmentation with quite flexible ways, right? So, or you can give it point prompt, you can give it bounding box prompt, you can give it like the text prompt, like just segment the, for example, a white Persian cat, this kind of prompt, right? So it can solve a huge part of the problem. And it's interestingly, it can also solve the image tracking problem. You give a video as a input, and then you find one of the object, and it can help you to track throughout the video. So it can having quite interesting performance, but it's in some of the cases, it's still quite understanding some of the rare concepts. Sometimes if you say stomata, I'm not sure if it works now, but previously it won't giving a very good performance on those rare classes. Because when you are training the language branch, it can also having some of the bias towards all those kind of frequent words, but with those less appearing words, so it will having less knowledge about it. But this also can be mitigated through different fine-tuning strategies, especially the parameter efficient fine-tuning by using techniques like LoRa. In this case, you can use a limited number of images to fine-tune this kind of foundation models to achieve the results that you want. So now let's move on to our second part of today's talk. I guess I have 10 minutes left, so I will quickly go through this part, right? So global bit full semantic segmentation. So in the morning, then just use the global bit head detection as the example. So global bit detection is the first version of the global bit dataset. So back to then, we can see that we have labeled this much of bit head and from those kind of high resolution images. And then it is a collaboration worldwide rather than from a single country. So now we are trying to, last year, the year before, we are trying to think about moving from the detection to the segmentation. Let's have a look of the right bottom corner. So this is the difference, like in between, right? So on the first image, this is global bit head detection. In this task, we are trying to find the bounding box surrounding those bit heads, right? But now, in the latest project, so what we are trying to do is assign the pixel level label to each one of the organ appears in this image, right? So that's the difference. And then we did do the diversity analysis of our data set, right? So we colored it into different growth stage, and we colored it from the different institution. As you can see, the difference between each one of the growth stage and the difference between each one of institutions are actually quite different. When you have a data set, only you can have such kind of diverse distribution. Your model trained on it can having like better generalization capacity. But we also having some of the limitations for the data set because of the nature of the weight growing, right? So when we label it, we notice that the percentage of the STEM class is very limited, as we can see that on the red bottom corner. So this is a histogram of each one of the different classes. As we can see, we only have very limited number of the STEM pixels. That's probably driving the leading to why that STEM performance is not as good. So in our initial analysis, we also showcase some of the visualizations, right? So we see how good it can actually perform and looks like, right? So in the first column, it is the input image. Second column is the ground truth, and the third column is the what our model predicted, right? So as we can see, for most of the cases, the width hat, leaf, and background are doing pretty well. Most of cases, STEM are also perform well, right? So if we just simply telling from our naked eyes. One interesting phenomenon is about the background. as we can see, this on the case L is a classic green on green problem, right? So those are V's and actual wheat leaves, right? But our model after training can successfully tell the difference on this green on green problem. It can automatically regard the V's as the background. And we are trying to find out if this scenario is only single cases or it always happens, right? So we sampled more wheat cases for the visualization, right? So and then we can see that it's really had this kind of ability, right? So to exclude the wheat on the class of interest. But as we mentioned, so we on our initial analysis, we do find some of the limitation of the baseline method, and then that's why we hope a global wheat food semantics segmentation competition. This competition is open to worldwide participants. So I won't go to a great detail of this competition. I just want you to know that in this case, we adopt a realistic setting where we assume that vast number of the unlabeled images are available, but only very limited label data are available for the training. This is because with our field sensor, I believe everyone can capture huge amount of unlabeled data, raw data, but doing the actual annotation is really time consuming. So this is why we propose this kind of setting, right? And we also use the in and out of domain data for testing, in domain data for the validation. So what are those winning solutions sharing in common, right? So we just have this kind of summarize. So first, for the architecture selection, people are trying to use the mask transformer and seg former. And then all of the winning top 5 solutions are using the semi-supervised learning method. People using the pseudo labeling and teacher-student work, right? And then for the backbone selection, we also see most of people are following these 3 different backbones to train their model. And then most importantly, to achieve a better method, people are always using the ensemble method, which is leveraging the prediction from multiple outputs to finally formalize the prediction result. And then this is the solutions from the first place team. So the key motivation they argue is the devil is actually in the detail and minority. So this reflects our initial finding. That is, we have less stem pixels. That's the reason why we have a worse stem performance, right? So they have designed 3 different key stages. First stage, they're trying to propose a upsampler, trying to dealing with the resolution issue. And second, they're trying to do a sample reselection strategy, which tackles at the class imbalance issue. And second is kind of the ensemble strategy, which they using different test argument to produce the different output, right? And then they ensemble the different output to make sure the final prediction is more reliable. But in the meanwhile, because the augmentation is using the zoom in method, so we say that this is also trying to solve the resolution issues limitations. So due to the time limitation, I won't dive into the great detail of those 3 different strategies. In the end, so I want to say that there are more machine learning model, more machine learning resources available these days, right? So people are also trying to build up the wheat foundation models and also even crop foundation models, right? So in this case, so people grabbing the image, the training data across different continentals, and then they form this kind of over 2,000 genotypes, over 2.5 million images, using that to train the foundation model that can be used in different downstream tasks. For example, the wheat growth stage prediction, wheat disease prediction, those kind of also counting counting problem, detection problem, and also segmentation problems, right? So all of those different computer vision tasks can be solved with this backbone, right? So like this is also like the visualizations. So what they are trying to do is after they extract the feature from different backbones, right? So they do a PCA to project the original feature in the lower dimensional feature space to make sure that it can be visualized, right? So then by using those three top principal components to do the visualization, as we can see that the foundation model like FOMO for wheat can exhibits the clear boundaries of those crops and crop organs, which indicates it will make it easier to adapt it to the downstream task with less data required. So basically, that's all for my today's presentation. Hopefully, we can catch up some of the time. And yeah, if we have any questions, feel free to ask. Yeah, thank you.
Thank you, Zijian. We have time for a couple of questions.
Thanks very much. That was a wonderful talk. I was wondering what methods you use to detect weeds and to mask them out of your images, because we get a lot of weeds cropping up in real world situations. And I was just wondering how you mitigate those.
Okay, so normally we treat the detection method and the semantic segmentation method separately, but we do have the special case. Let's say we want to do some of the segmentation. So what we will do is we will have a foundation model ready, and then we using those annotated method with the parameter efficient fine tuning, things like LoRa. To LoRa, but this is a family of methods. We do have different things, and then to do the initial round of fine tuning, and then let's see if you have the large amount of the unlabeled data. In this case, we can also think about some of the semi-supervised method, like how do we leveraging those kind of unlabeled images. It's very important, the unlabeled part. Right, so by incorporating them, model can see more, can understand more, can generalize more. Right, so for the semi-supervised method, we will consider the teacher-student network and also the pseudo labeling. Pseudo labeling, it's interesting. Pseudo labeling can only work if you have a good baseline model, right? Or otherwise, you will see that all those kind of pseudo labeled is wrong, and then model learn from the wrong thing. But generally, that would be the initial step we took if we're facing some project like this. First, thanks.
No, do you have a question? No, you go first.
That was a really great talk. So just at the end, when you're talking about the PCA, sorry if this is a dumb question, but have you done any other transform methods to have a look-see in the sort of frequency domain or other ways to reduce the information before you do all this analysis?
So in this case, we did not apply the frequency space analysis. Yeah, but we did using some of the frequency-based method in other lines of research. But one of the frequency-based, it's maybe off the topic because we use the frequency-based method as a image augmentation strategy rather than a analysis strategy. But back to then, we trying to manipulate the low frequency and high frequency part of the images to bring up some of the augmentations to broaden the model's knowledge space. Yeah, but then it might have some of the resolution concern we can